extreme values, objectives. By the end of this lesson, you should be able to define extreme values, define absolute global extrema, define local and relative extrema, explain the difference between absolute extrema and versus local extrema, state the conditions for a function to have absolute maximum or absolute minimum, define and find critical points values, recite Fermat's theorem for local extrema, and finally to find absolute extrema of a function on a closed interval. Before we get started, let's do a quick review of intervals. So let's let a and b be real numbers. A closed interval includes the endpoints a and b, and graphically be closed points. So like right here, this is a closed interval. You have the closed endpoints. So this would, you'd say your domain goes from -1 to 2. I use brackets to identify it's a closed function. An open interval a, b does not include endpoints, right? So a and b here, you go from -1 to 2, but notice how they're open circles. So we do not include the endpoints. And then we have these half-closed, half-open sets, also known as clopen sets. It includes one endpoint or the other, graphically one closed endpoint and one open circle. So in this case, you have a closed on the left side, open on the right side. So it'll look like this, -1 and 2. 2 with the parenthesis. Right, and it could also be the opposite, other way around. Okay, so now we can define what extreme values are. Extreme values or extrema, singular extremum, of f of x are the maximum minimum values of the function. So there's like the maximum. Extrema is the maximum. So we have two types. We have absolute global extrema and we have local relative extrema. Let's focus on absolute global extrema first. So absolute global extrema is the absolute minimax. So what they say is let f of x be a function found at interval I, little asterisk, that's usually I is the entire domain, don't worry about it too much, with an a in the interval. So there's some value in the interval. We say f of a is the absolute min if on f of x, on the interval, if that value, f of a, is lower than all the rest of the values on the interval. So a is the lowest value on that interval. Another way to think about that, an absolute min is the smallest y value on I. So think of a picture like this. I have a little parabola right there. That'll be the absolute min or global min, right? It's the smallest y value in the whole interval. Absolute max is the exact same idea. You have some value. It's f of a is actually the biggest value, greatest value on f of x on the whole interval. Another way to say it, absolute max is the biggest y value. So if you think about an upside down parabola, that point right there is the absolute max, right? It's by far the biggest point on that graph, on that function. So how's that different than local relative or local relative extrema? Well, we say f of x has a local minimum at x equals c if f of c is the minimum value of f on some open interval containing c. What does that mean? That means if I give you a picture like this, the local min is the smallest point in the little area. Sometimes they say a little neighborhood. So like here, you can think about this point right there. Right, in that little area, it's the local min. There's points over here that are actually lower, but in this little area right there, that's the lowest point. Likewise, like right here. I mean, I didn't draw the best picture. Apologize. But again, that'll be the local min right there. And the little area right there is the lowest point. You know, there's lower points, like here, there. In that little area is the lowest point. So we say that the local min are the valleys. If you think about like hills and valleys, like that's the valley, right? So the low point of the hill. Okay. Likewise, local max, it's the highest value, the highest y value in the little interval. So as you probably could guess up here, that'll be my local max. And right here could also be local max. Right? They're the highest points in the little area. There might be higher points, like this graph keeps on going, so there actually is a higher point than that point right there. But in the little area, those are the local max. So we said local maxes are the peaks. If you think about a hill, we have peaks and valleys. Right? All these points right there are local maxes. all the points right here are local mins. Quickly before we move on, a couple key things. Notice absolute max or min, there can only be one. Can only be one of these. At most one, right? You can have absolute min, you can have absolute max. You can't have two absolute max. That makes no sense. Absolute max means like that's the highest point. So there's only one of these at most. There's only one of these at most. But if you saw right here, like the local min and max, there could be more than one. This point, my graph I showed right there has 3 local maxes and 3 local mins, right? Since it's just linearity, you can have more than one. So you can have more than one. Oh, one last thing, these must be real numbers. Hashtag real numbers. That just means you can't have infinity or negative infinity. That's why if I scroll up here, this has absolute max, but no absolute min. So the absolute min is infinity or negative infinities, and you can't have it. It has to be a number. So must be real numbers, no infinity or negative infinity. Okay, let's make it a little more concrete now. Given the graphs of f of x, identify the absolute extrema and any local extrema. So for each one of these, we're going to find the absolute max, absolute min, local max, and local min. Voila. So let's actually do a problem here. So on this first, on the left one, we want to find absolute max. That's the highest y value you can possibly find. So look at this graph here. The highest y value, if there is one, is right here, right where the vertex is. That point would be x of 2 and y of 3. So now our absolute max is the y value. So we would say 3, which equals f of 2, right? It happens at 3 or f of 2, right? F of 2 means the y value at 2, which is just 3. Absolute min, we need the lowest y value. Now, my lowest y value is negative infinity. When we talked about earlier, it has to be a real number. It can't be infinity or negative infinity. So there actually is no lowest y value. It keeps on going on forever. So there's no absolute min, none. Now we want local max. So that's the highest and low area. Well, the only place where there's like a little peak, you might call it, is right there, which is our absolute max. That's fine. It could be both. So our local max is also our absolute max. And likewise, there's no absolute min. There's also no local min anywhere. The lowest I see is here. I don't see any valleys, so there's no local min. Let's look at this one. It's a little different story here. Absolute max. Highest I see are arrows. So again, that's infinity. That's not a real number though, so none. There's no one number where we stop at. It goes on forever. Absolute min, that changes. Right, we want the lowest value. The lowest value is like right here. Let's say a -1 and -4.5. So my lowest value is -4.5. Remember the y value? So I get to say -4.5 equals f of -1. Now here's where it gets interesting. Local max. Right, so again, I have no absolute max. It goes on forever. But there is a local max, right? Is there a peak? Is there a highest point in this little area? And that'll be right there. Right? That's the highest point in this little area. That's a local max. Not absolute max, because this graph goes on forever, but a local max for sure. So it looks like -1 y value equals f of 0. There's only one local max. But look at the local mins. Right, local mins are the little valleys, the little bottom curves. We have one right there. It looks like, we'll say 1 and -2.5. And we also have the one from before, the absolute max, right? That's also local max. It happens to be both of them again. So you have two local mins. We have -2.5, which equals f of 1. That says f of 1. And then we have -4.5, which equals f of -1. So let's look next. Do all functions have extreme values? No. Right? So here's the 3 examples of things that have no extreme values. Right? So like, is there an absolute max here? No, there's not. This graph goes on forever. There's no number it stops at. Is there an absolute min? No, there's not. The graph goes on forever. So no extreme values. Here, you kind of say, oh, maybe right here, maybe there's one right there. But it's not a local max because there's points right here that are above it. So it's not a local max, not a local min because there's points below it. This is actually what's called a stationary horizontal inflection point, which is not an extreme value. So no, again, no extreme value. So there, no extreme, here, no extreme. Then right here, like, oh wait, that has to be one. That's that local max. But notice it's an open circle. There's no value there. There's no number there. Remember, our local max has to be a number. So again, no extreme values. There's actually no value that's a max value. Okay, let's look at a theorem. Theorem. If f(x) is continuous on a closed interval ab, then f(x) has both an absolute max and an absolute min. This is a very important concept we're going to use a lot in this lesson. And all this says is this, right? If it's a closed interval, if we have both endpoints, then there must be a max or min. There has to be. Let's draw a quick example. So the graph looks like this, right there. 1, 2, 3, 4, and -2. Right, so a graph like that. If you notice there's no local min or max, But what's the absolute max? Well, it's a closed circle right there. My absolute max is right there. It's 4, or f equals 3, f of 3. Right, what's my absolute min? Well, it's the lowest point on the graph. Since that is a closed circle, that counts. So it's my absolute min is -2 at f equals -2. Okay, so let's draw another graph. What if I did a graph that looks more like this? Is there an absolute max or min? Yeah, there is. My absolute min, again, these don't go on forever. They're end. It's a closed interval. My absolute min is the lowest point right there. So it looks like my absolute min is -2 or f of -3. And my absolute max, and in this case, it's not one of the endpoints. It's a point in between it. It's this guy right there. Ooh, why can I draw a better picture? It looks like it's 2 and 1, 2, 3, 4, 5.1. So my absolute max is 5.1. Again, the y value, or f of 2. Right. So that's the key thing about this. If it's closed interval, then it must be absolute max or min. Right? And it could be the absolute max could be the endpoints. Max and min could be the endpoints, or it could be a point in between. It could be a local max, local min that happens to be the highest value or lowest value. So very important concept right there. Next, let's talk about critical points. So a critical point is any number c in the domain of f is called a critical point if either f prime of x equals 0 or f prime of x does not exist. So that's a critical point, right? Where the derivative equals 0 or the derivative does not exist. Very, 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 very important concept. So how do you find critical points? Well, it's just like it sounds, right? If you want to find a critical point where f prime of x equals 0, well, you set the derivative equal to 0 and solve for x. It's very straightforward. If you want to find where it does not exist, find out x value where the derivative is undefined. Most of the time, it's set the denominator equal to 0, if possible. One thing you want to check out, sure, make sure your x values are in the domain. So, like, let's say you solve for x here. Let's say my domain is, I don't know, -2 to 5. And then when I solve for x, when I do this guy, I get x equals -3 and 4. Well, 4 is in the domain, right? 4 is between 2 and 5, but -3 is not. 3 is too low. So all that says is make sure when you check your x values that they're not automatically critical points. You gotta make sure they're in the domain of the original function. No, let's do some examples. So I want to find the critical points of all the following. So let's start with this one. Right, so if I want to find the critical points, I'm going to set the derivative. First, I'm going to find the derivative of this guy. So let's say 6x minus 6. Now, this one, there's nowhere it's undefined, right? It's just a polynomial function, so it's always going to be defined. So we just got to figure out where it's equal to 0 at. So let's set the derivative equal to 0. So I get 0 equals 6x minus 6. Do a little math. X equals 1 is my critical point. Now you might notice that there's a little flaw in the notation. Critical points, usually points are an x and y value. For critical points, we actually only ever care about the x value. So it's just like inherently known. Oh, where's the critical point at? X equals 1. Let's do the next one. G of x equals that. So let's take a derivative. So I'm trying to look for the critical points. Bring the 2/3 down, subtract 1 off, common denominator. I get 2/3, 2 square root fractions, not me. Negative 1/3. So let's rewrite that as 2/3 x to the 1/3. Now, so that's my derivative. Right? If I want to find my critical points, I got to find two things. One, where does it equal 0? Now, here's a trick to solving this. Anytime you want to set a fraction equal to 0, all you do is put over 1, cross multiply, and I get 2 equals 0. So this has no points where the derivative equals 0. It's not a thing, right? So if I try to solve this, really all you care about is the numerator. Or you could cross multiply and you get 2 equals 0, which is not true. So no critical points in that phrase. No point where the derivative equals 0. So the derivative never equals 0. But that's not the only critical point, remember? It's also where it's undefined, where a derivative is undefined. So how do you figure out something's undefined? You set the denominator equal to 0. So let's do it that way now. I'm going to set this guy equal to 0. We'll solve it there, divide by 3. Right, take the cubed power of both sides, and you get x equals 0. Is that in the domain? Well, if we plug it in, does it work? Yeah, 0 to 2/3 is 0. It works, checks out, there's no issues there. So that's my critical point for this problem. So my critical point in this one is not where it equals 0 at, not where the derivative equals 0, it's where the derivative was undefined. So very important. You gotta check both types, right? Where it equals 0 and where it's undefined. We don't have to worry about that here, right? This one was never undefined. It's just a polynomial, so it's always defined. This one's a fraction, so sometimes it's undefined. Next one. So this one might take a derivative. Oh, look what's going on there. Quotient rule. So uv, so derivative of the top, 2x times the bottom, x minus 3, minus the derivative of the bottom, which is 1 times the top left alone, all over the bottom squared. So that is my derivative. Let's simplify it a little bit. 2x squared minus 6x, to shoot this negative, minus x squared. So my derivative, h prime of x, is going to equal x squared minus 6x over x minus 3 squared. Now, just like before, let's find out let's find the critical point. So first, I'm going to set the derivative equal to 0. So I'm going to get x squared minus 6x over x minus 3 squared equals 0. Again, two ways to think about solving this. One way is just worry about the numerator. Just solve the top. If the top's 0, then the whole thing is 0. So all you have to do is that way. If you're not comfortable with that, just set that over 1, cross multiply, and those will cancel out. And these will cancel out, and you just get 0 equals x squared minus 6x. Factor it to solve, because it's quadratic. We both have an x. Split and solve. X equals 0, and 6 are my critical points. Now, are those in the domain? Now, remember, the only thing you cannot have, if you look at this function, is 3. Right? So the only thing you can't divide by is 3, because then that makes it 0. So those are both good. If I plug in 0, I get a number. If I plug in 6, I get a number. So those are some of my critical points. That's the first way, though. That's where set the derivative equals 0. We also got to find the ones where we set the derivative is not defined. So you set the denominator equal to 0. Right, so where it's undefined. So x minus 3. First, to label these. So I'm going to set the bottom equal to 0. Solve it, square root both sides. You get x minus 3 equals 0. You get x equals 3. Now this one, though, if I plug it in, I get 9 over 0. Can't do that. It's not a right number. Right, the one thing you couldn't be was 3, and I got a 3. So this is not a domain, so it's not a critical point. My only critical points are these two guys right here. Let's talk about Fermat's theorem on local extrema real quick. So his theorem says this, Fermat's theorem. If f of c is a local max or min, then c is a critical point on f of x. For example, let's say I give you a graph that looks like this. Let's make it a little fun. That's a cusp. Right, so there's my graph. Right, where the local max and min at? Well, my local max is right here at -2. X equals -2. I have a local max right there at x equals 2. Right? If I was talking about my function, that's where my derivative equals 0 and defined, right? Here, that's where my derivative equals 0 because you have a horizontal tangent line. And here, my derivative is undefined to cusp. So, if you have a local max or local min, those are your critical points. Alright, just to reiterate, notice how this point right here, f prime of 2, would be does not exist because it is a cusp. And over here, f prime of negative 2 would equal 0. Right, so that fulfills the obligation where, hey, if the derivative equals 0, then it's a critical point. If the derivative does not exist, it's a critical point. But do watch out, very important right here, it does not go both ways. If C is a critical point, it does not necessarily mean it's a local max or min. I kind of mentioned this earlier. This guy right here is what's called a horizontal inflection. Some other words for it, but in general, it's horizontal inflection. That's also a critical point, but it is not a local max or min. So if I see something like that, just because you have a critical point does not necessarily mean max or min. There's actually a little bit more ways to get critical points. So again, max or min implies critical points, not necessarily the other way around. Now let's combine all these ideas to find extreme values on a closed interval. So let's see. Assume that f of x is continuous on closed interval AB and let f of c be a minimum or maximum value on AB. Then t is either critical points or one of the endpoints. So all it says is this. If I give you a graph, let's say it looks like this. On the closed interval, so notice I have a closed endpoint. So to that effect, so again, notice it's a closed interval. Then then this thing must have an absolute max or min, and it's either going to be an endpoint or it's going to be a critical point. So to find a max or a min, absolute max or min, you have to check the endpoints plus the critical points. Very, very important. Right, if you look at this graph right here, right, it's a closed interval. So what's the absolute max? In this case, happens to be an endpoint. What's the absolute min? Happens to be local min or max. Remember, the way you get the local min and maxes are from the critical points. The way you get the endpoints are from the endpoints, hence the name. So if you want to find an extreme value, max or min, on a closed interval, very, very important. You got to check the endpoints and the critical points. You have to check both. Right, so this is only one picture. I can also draw a picture like this. Right, in this case, again, it's a closed interval, so that's why it's closed. The max happens to be a local max, and the min happens to be a local min. Right, so in this case, it's not the endpoints, but it very well could be two examples here. One where the endpoints do play a factor, and one where endpoints don't play a factor. In both cases, when I want you to find absolute max or min, extreme values, I cannot stress it enough. You check endpoints and critical points. Remember how you find the critical points? You set the derivative equal to 0 to find those guys. Endpoints to give to you. They're going to give you the endpoints, A and B. Critical points, you got to set the derivative equal to 0 and find it. So just to reiterate that, we'll give you a step method here, right? Steps for finding extreme values on a continuous function on a closed interval A, B. So if I tell you find the extreme values, find the max or min on a closed interval A and B. So first you find the critical points. And we do that by setting derivative equal to 0 or undefined, right? So we want to find critical points. You set the derivative equal to 0 or undefined. Remember, the way you set it equal to 0, you essentially set the numerator equal to 0. And how do you find undefined? You set the denominator equal to 0. So you have a fraction, you set each one equal to 0. Okay, then we have to figure out what f of x is on both endpoints. All that means is plug your points in. Plug critical points and the endpoints into the original function. That's all that means, right? You have your x values, your critical points, you have your x values from the closed interval, plug them into the original function. Whatever the highest value is your max, whatever the lowest value is your min. You can write out times the max or min. That's all it is, right? That's all it is. You find your critical points, you find your endpoints, you plug them back into the original function, whatever the highest value is your max, whatever the lowest value is your min. One side note, if it's on an open interval, say we're like, hey, A, B, what does that mean? You could skip endpoints because it doesn't have any. Just find critical points. Right, so that's if it's on an open interval. If it's on an open interval, you don't have endpoints, so you just find the critical points. If it's on a closed interval, it's endpoint, critical points plus endpoints. Okay, let's do a few examples real quick. Find the absolute maximum of this thing on the open interval 0 to 6. So remember, absolute max and min. You gotta find critical points plus endpoints. I already have the endpoints. They give them to me. So 0 and 6. That's my curly bracket. Don't laugh. So I got for my critical points. Remember the way you find that? You set the derivative equal to 0. That's set. So here's my function. Let's find the derivative. That is 6x squared minus 30x plus 24. We're going to set that equal to 0. Remember, make your life easy. These all divide by 6. Work smarter, not harder. And this is a lot easier to factor. It's x minus 4, x plus 1. X minus 1, sorry. So x equals 1 and 4. Now again, you want to make sure, these are just my critical points. I'm not saying that's my answer or anything like that. You want to make sure these fit in the interval. Right, my interval is 0 to 6. I have 1 and 4. So they actually do fit. So what I'm going to do next is, I'm going to check all those guys. I got to find out I want to figure out what f of 1 is, what f of 4 is, check my endpoints, what's f of 0, and what's f of 6. Alright, so all I'm going to do is, once I have my critical points and my endpoints, I plug them all into the original function. Whatever the highest is my max, or the lowest is my min. So help you out, I did the work already. So f of 1 is 18, just plugging 1 into this guy. F of 4 is negative 9. F of 0, that's easy, it's just 7. F of 6, plug it in. I got 43 when I did it. So, let's look at this. My absolute min is right here. My absolute max is right there. Which you can tell on the graph, right? We don't always have the graph, but the graph you can see my absolute min is right there. My absolute max is over here somewhere. So, absolute min is negative 9. Absolute max is 43. Let's move on to the next one. Next one only wants to find the absolute max, right? Same idea, find critical points plus endpoints. I already have my endpoints, so negative 1 and 2. I got for my critical points, right? So I'm going to set the derivative, take the derivative set equal to 0 or undefined. So the derivative of this guy, well, derivative of 1 is 0, good. Derivative of this one is a chain rule, bring that down, subtract 1 off. I get negative 2/3 x minus 1. Subtract common denominator, negative 1/3 times the derivative of the inside, 1. Let's make it a little prettier so we actually do some math. So I get negative 2/3. I'll move that down. I'm always bad at that. So that's my derivative. Now remember, we have to do it two ways. How do you find critical points? You set the derivative equal to 0 or undefined. If I set this guy equal to 0, right, that's just in the top equal to 0, which doesn't work. There's no variable there. So that's not going to happen. But where's undefined? That's where you set the denominator equal to 0. So we're going to find that one. Where is this guy undefined? So all we have to do is set the denominator equal to 0. Right, just by looking at it, you should be able to tell it's just going to be 1. That's going to set that. That's to make that 0. But let's go to the rigmarole. Divide by 3. You get this. Right, cube both sides. You get x minus 1 equals 0. So x equals 1. Again, you can really skip that. You can tell by looking at it, it's x equals 1. So this is my critical point. Don't forget, I'm not done. I want to find the max value. So first I need a y value, but also I'm going to not only check the critical points, I got to check my endpoints right here. Right, so I'm going to check negative 1, 2, and x equals 1. And by the way, 1 does fit within my endpoint, so it is a good one to check. That's all we're going to do. All we're going to do is figure out what f of 1 is, what f of my negative, my endpoints here, and f of 2 are. Whatever the highest one is my maximum. So it's easy to plug them in. If I plug this in just real quick, 1 minus 1 minus 1 to the 2/3, that's a 0, so I just get 1. Plug this one in, 1 minus negative 1 minus 1 to the 2/3. That's 1 minus negative 2 to the 2/3. We'll work on that later. And then f of 2, 1 minus 2 minus 1 to the 2/3. 1 minus 1 to the 2/3. Well, 1 to any power is just 1, so 1 minus 1 is 0. Remember, we're looking for the max. So right now I got 1. I got 1 minus negative 2 to the 3rd. And I got 1 minus 1 equals 0. Well, that for sure, 0 is definitely not it. So it's between 1 and 1 minus negative 2 to the third. So we got to think about this logically. I'm going to take the cube root of negative 2, some small number, then I'm going to square it. That's going to make it positive. So this is going to be 1 minus some number. Right? Well, this is 1. Well, I should say 1 minus a positive number. So that's going to be less than 1. Well, this is 1. So my max is actually 1. Right? And all that's because I have 1 here, and over here I have 1 minus some positive number. How do I know it's going to be positive? Because it's squared. And when you square something, it's always positive. So it's 1 minus some positive numbers, going to be less than 1. So 1's the max. Okay, one last one. We're done. Find the x values of the absolute max and min of f of x equals x squared minus 8 natural log of x on 1 to 4. So remember, absolute max or min, critical point plus endpoints. Cannot stress that enough. So I already have 1 and 4 for my endpoints. I just got to find the critical points. And then I can plug them all into the original function, whereas my highest is my max, where lowest is my min. So, remember the way you find critical points? Set the derivative equal to 0, or undefined. So I take the derivative of this guy. Derivative of x squared is 2x. Derivative of 8 natural log is negative 8. Remember, derivative of natural log is 1 over x. So I get this. Let me write it a little nicer right there. I get 2x minus 8 over x. So I gotta do two things, right? So first I gotta set the derivative equal to 0. So 2x minus 8 over x equals 0. So I get 2x equals 8 over x. Just added that to both sides. Cross multiply. 2x squared equals 8. Divide by 2. X squared equals 4. Square roots. X equals plus and minus 2. So those are some critical points I have. We'll check that out in a second. I still gotta do where it's undefined. Right? Well, look at this right here. Where's undefined? Well, you can't divide by 0. So I also have x equal to 0. Now here's the thing. Remember what I said earlier? Look at your domain. 1 to 4. Of all these critical points I found, only one of them actually fits. Right? Only one of those actually fits in the domain. 1 to 4. And that would be positive 2. 0 doesn't fit. Negative 2 doesn't fit. Just 2. So all the ones I'm going to check are actually these. My endpoints, f of 1, f of 4, and then my critical point, which happens to be x equals 2. Only critical point that's in the domain. Right, again, you could check these, but they're not going to be right. They might even get a higher value, but not right. It has to be in the domain, interval of 1 to 4. So only ones that fit between 1 and 4. So that's why it's only 2 from this set, and then the actual endpoints. We plug them in. f of 1 we can actually do by hand. Just plugging it in. 1 squared minus 8 times natural log of 1. Remember, natural log, which all know is 0. So I get 1 minus 8 times 0, which is just 1. f of 4 and f of 2, I actually need a calculator because I do not know what natural log 4 or 2 is off the top of my head. But put in your calculator, you get this and this. Oops, sorry. Negative 1.545. Question was to find the absolute max and min. So my absolute max is f of 4 at 4.9. My absolute min is this. So absolute max 4.909 and absolute min negative 1.545. And that's the lesson.